Now we can also solve quantum oscillator. Okay, so quantum oscillator has the potential term, which is half x squared. Okay, now it is non-dimensionalized, so it is half x squared. Now the initial condition here is this one, this blue curve, and it is superposition of the ground state and the first excited state. Okay, so I put two of them, the ground state and the first excited state, and I choose large enough box. Okay, so we can't take infinite box, but we take large enough box. So it's minus 10 to plus 10. So you remember that it's my dimension is order 1 for the Gaussian peak. So it's a function of time. We get a red curve is t equal to 1 unit and t equal to 2 units. I get green curve. And exact solution is the dash curve. The dash is the exact solution here. So exact solution again is approximately on top of the numerical solution. And this for the real wave function, the real part of the wave function, imaginary part of the wave function, the absolute wave function. Okay, so we get basically pretty good numerical solution. The numerical solution is pretty close to the exact solution. Okay, here you don't see the merit because we can get the exact solution for them. But imagine that we have a quantum dot, which is pretty complicated, elliptical quantum dot. Okay. Now I want to solve for the wave function inside, and getting an analytical solution is quite complicated. Okay. Or imagine that this potential is not zero outside, but it is gradually decreasing outside. So that can also be solved using numerical method, but not so well by analytical method. Now, the last equation I want to discuss briefly is called Gross-Pitaevskii equation. Okay, so this equation for superfluid or superconductivity, where it's not easy to, I mean, this is not like hydrogen atom or oscillator. Okay, so there are many electrons, and they are interacting with each other, and that leads to complex quantum interaction, and that is the reason for this term, G mod psi squared psi. Okay, so it's a non-linear term. This, in fact, is a non-linear Schrodinger equation. Okay, is a high power higher than 1. Okay, so this term is usual, but this is a non-linear term. And we can follow the same scheme like what we did before. You know how to solve this part, right? V psi, which is V psi hat. Now here, I'm just going to take psi squared psi, mod psi squared psi hat. Okay? So hat is Fourier transform. So this is the only additional term, and it just comes there. So you non-dimensionalize it first and solve it numerically, no problem. Here we need to compute this term using again Fourier transform. Spectral method is accurate as long as we have good Fourier transform routines, we can solve all these. Of course, it takes time. If it's 3D field, then it will take long time, but it's all doable. A spectral method has one disadvantage, that we require the box to be nice. I mean, in the sense, it should be a box or periodic box or a box with boundary condition which is 0 at both the ends. Like elliptical solution, doing Fourier transform is not easy. In fact, we don't solve using Fourier transform for these sort of problems. Okay. Because we can't do Fourier transform for arbitrary geometries. We need function to be periodic. Okay, and So that's a limitation. Complex geometries cannot be done by, can be done by special Fourier transforms, but they're practically impossible in practice. Okay? And but is very accurate. Advantage is accuracy. All right, so thank you, and we stop here for spectral method discussion. And I just wish you luck for solving some of the problems. You can just write codes and test it out, test these ideas.